Okay, so first question we're going to take a look at is finding the real zeros of that polynomial. So that means finding the roots, or where it crosses the x-axis. Now that one is probably doable with factor by grouping, but there will be some on the test that are not. So let's start by finding possible roots that could work. Anyone remember the name of that theorem that would give us a list of possible roots? That's 3 letters. Yep.
Rational root.
Yep, rational root theorem. So using the rational root theorem, first thing we're going to figure out are the p's and the q's. What are all the factors of the constant in this case? Yeah. So factors of the constant would be the factors of the number 9.
1, 9, and 3.
Yep. So positive or negative 1, 3, 9. And the factors of q are 1 and 2. Those are the factors of the leading coefficient. And then to get all the possibilities, we write all the different p's over the q's. So we've got 1 over 1, 1 over 2, 3 over 1, 3 over 2, 9 over 1, and 9 over 2. Okay, so we got a lot of different options. How can I narrow this list down? Yeah.
You can graph the equality.
Yep.
Equality equation.
Equation, yep. So we're going to graph it. So there's our graph after we type it in. And we're going to see if any of the ones in this list seem close to that. Okay. Does anyone think they see one that looks pretty close? Yeah.
Positive 1/2.
Positive 1/2? Okay, let's check it before we use synthetic division. So I'm going to do trace to 1/2, and yes, 1/2 is a root. So now what we want to do is take out the factor x minus 1/2, and we're going to be left with a quadratic, which we're going to solve to get the other 2 answers. Looks like 3 and negative 3, but we'll get to that. All right, so we're going to divide through synthetically by 1/2. Okay, what would be the numbers on the outside, or the inside, when I do my synthetic division? Yeah.
2, negative 1, negative 18, 9.
And 9. Okay, so bring down the 2. What's half of 2? Yeah.
1.
1. Add those up. Half of 0 is 0. Add those up. What's half of negative 18?
Negative 9.
Yep, negative 9. And add those up, and there's my remainder. Okay, so we know 1/2 is a root. Let's see what else there is. Now, you're going to focus on the quotient, but that's going to be easier to work with because the exponent now is only going to be a 2. So we have 2x squared plus, we don't even need to write plus 0x because it doesn't do anything, minus 18. So now, you've factored out one of the factors. Now let's find the roots of this. Set it equal to 0. This time I can factor out a GCF. What's the GCF between those 2 terms? Yeah.
2.
2. So let's factor out a 2. We're left with x squared minus 9. And x squared minus 9 is going to factor and break down into 2 factors. How does x squared minus 9 factor? Yeah.
X minus 3, x plus 3.
Perfect. X minus 3, x plus 3. And now I'm down to just linear factors which are the easiest factors to figure out the roots from. So what number would you plug into the first factor to make that one 0? 3. And the second factor? Negative 3. Yep. Now, if we had gotten to a quadratic that we couldn't factor, what formula can you use if you have to? Yeah?
Quadratic.
Yeah, you can use the quadratic formula, and you could have even used the quadratic formula when you got to this step. It's just for this problem that's a little overkill. You don't need it. Okay. So any questions on finding the roots there? Okay. Okay, for the next problem, we're going to go back and look at the same question we did the first time. We're going to divide the 2x cubed minus x squared minus 18x plus 9 by x minus a half. And we already know what we're supposed to get for an answer. That's going to be my quotient. That'll be my remainder. But this time we're going to try it with long division. So the first step is to divide x into 2x cubed. What do you get when you divide x into 2x cubed? Yeah.
2x squared.
Yep, 2x squared. We're going to multiply that back out. So it's going to give me 2x cubed. And then 2x squared times negative a half. Well, positive times negative is a negative. And half of 2 is 1. So I get negative x squared. Now, when we're doing long division, what do we do with these columns? Different than synthetic. Yeah.
Subtract.
Yep, we're going to subtract them. So the 2x cubed minus 2x cubed is gone. And what's negative x squared minus negative x squared?
0.
0, that's also gone. But we already knew that was going to be gone because we had a 0 right there. So we're on the right track. So now bring down your next term, negative 18x. And let's do this out. Actually, you know what? We can bring down the next. We can bring down both terms because this is going to be our last step. Okay, so divide x into negative 18x. What's negative 18x divided by x?
Negative 18.
Negative 18. Yep, multiply it back out. Negative 18x. And what's negative 18 times negative a half?
9.
Yep, positive 9. And subtract. And what's negative 18x minus minus 18x?
0.
0. What's 9 minus 9?
0.
0. And that's my remainder. So my quotient is 2x squared minus 18. And my remainder is 0. It's exactly the same thing we got in synthetic division. But that's how you do long division. All right, so the next one we're going to take a look at is we're going to determine if 3 is a root. Now, in this particular case, I could just plug in 3 and see if I get 0. Okay? I know that if I plug in 3, I'm going to get 3 cubed is 27 minus 12 plus 1. It's not 0. So 3 is not going to be a root. But we're going to do it a different way because one of the skills in this problem is going to be the rational root theorem. The remainder theorem. And you're going to have to do the remainder theorem on the test or something. So rather than checking if 3 is a root, what would be the factor that would have come from?
X minus 3.
Right, that would have come from a factor of x minus 3. So I want to check if x minus 3 is a factor of x cubed minus 4x plus 1. Now, if something is a factor, when you divide it in, what do you get for a remainder?
0.
You get 0. So let's divide this into that. But let's just use the remainder theorem to check the remainder. And then that'll tell us whether or not that is a root. So the remainder theorem says you have x cubed minus 4x plus 1. You take the number that's after the minus sign and you fill it into the top. When you do that, it will give you the remainder when you do out the long division. Okay, so let's do it. So we're going to get 3 cubed minus 4 times 3 plus 1. Okay, what's 3 cubed?
27.
Yep, 27. And 4 times 3 gives me 12. 27 minus 12 is going to be 15. And what's 15 plus 1? 60. Okay. So when we try to divide x minus 3 into x cubed minus 4x plus 1, we're going to get a remainder of 16. What does that mean about x minus 3?
It's not a factor.
X minus 3 is not a factor. What does that mean about the 3? It's not a root. Perfect. So determine if 3 is a root. No, 3 is not a root in this problem. All right, so the next one we'll look at is finding a polynomial with given roots, in this case 4 and negative 2. So the first step is, again, to work backwards and tell me if 4 is a root, what would be the factor that it came from?
X minus 4.
Yep. And if negative 2 is a root, what would be the factor that that came from?
X plus 2.
X plus 2. So now when we FOIL these together, x times x, what's that going to give me?
X squared.
X squared. What's 2x? Take away 4x.
Negative 2x.
Negative 2x. And negative 4 times 2?
Negative 8.
Negative 8. So if I graph that, where should it cross the x-axis?
It should cross that at negative 2 and 4.
Yep, it should cross it at negative 2 and 4. And it does. All right, so the next question, we're looking to see if a function is continuous or discontinuous. Okay, how about the first one? Would that be a continuous function or discontinuous?
Continuous.
Yeah, how come?
Because it doesn't like stop at any point. Like you can put your pencil on it and keep drawing. And there's no point where you have to lift it.
Yep, so this one is continuous, exactly. How about the second one? Continuous or discontinuous?
Discontinuous.
Yeah, that's discontinuous because it's broken into 2 pieces. How about the third one?
Discontinuous.
That's also discontinuous. And because you'd have to pick up your pencil as you're drawing it, let me add one more. Let's look at this one. It's a graph that has a hole in it. Continuous or discontinuous?
Discontinuous.
That is discontinuous. That's an infinitely small hole in the graph. But a hole is a discontinuity. Yep. Okay, so the next question is not only describing if a graph is continuous or discontinuous, but where. So this one definitely is discontinuous. And when I ask you where, I basically want to know what number would you have to pass through. And if you tried to do that, you'd have to lift your pencil and then put it back down. So what number would you have to pass through here and it would be discontinuous?
Negative 3.
Yeah, negative 3. So it's the point where you'd have to lift your pencil up and then put it back down again. Any questions on that? Okay. Okay, so next question we're going to look at is finding the EBM. And remember, the EBM is the end behavior model, and it's a simplified version of what we're looking at. What I think I'm going to do, because in class, let's see, did we look at ones that had fractions? Or did we, no, I think we just looked at ones that were not fractions. So that's in another class I'm doing. Let's just look at just the tops then. Okay, so the EBM is what basically controls the entire polynomial. What would be the EBM of 3x plus 1?
3x.
Yep, that's going to be the term that controls everything. And what would be the EBM of 2x cubed plus 3x plus 1?
2x cubed.
Yep, 2x cubed. Okay, it's the leading term with the highest exponent. Now, let's take something similar to that, and let's not only describe the EBM, but now the end behavior itself. So let's describe the end behavior. Say you had negative 3x squared plus 2x minus 4. So all you have to do is focus on the EBM, and then once you're focused on that, there's two things we have to look at. What's the EBM in that one?
Negative.
Yep. Yeah.
Negative 3x squared.
Negative 3x squared. And the two things we have to focus on are the negative 3 being a negative and the 2 being an even. What's the end behavior when you have an even exponent and a negative number in the front? Yep.
I think it's down up.
When it's different directions, that's always for an odd exponent.
Oh, so down.
That is a down and a down. Yep. And let's describe it also in limit notation. So the limit of f of x as x approaches negative infinity, and the limit of f of x as x approaches positive infinity. So on the left, what's happening to y as x heads further and further to the left?
It's decreasing.
And what's it decreasing to?
Its values.
Well, what is it getting closer and
Oh,
closer
negative
to?
infinity.
Yeah, negative infinity. And on the right, what's happening to the y values as x heads to the right on this graph?
And it's also getting closer to negative infinity.
It's also getting closer to negative infinity. So you should be comfortable with describing the end behavior either using the arrow notation or limit notation. Either way. All right, so the next one we're going to look at is solving an inequality. A little too complicated to solve for what we know with algebra, so we're going to do it graphically. So to do it graphically, where would I put that in on the calculator? I could put the left side in under what?
Y1.
Yeah, we could put that in y1. And what about the right side?
Y2.
Yep, y2. So I've typed those in y1 and y2. Okay, we've got our graph. Okay, and let's take a look. To kind of color code it, that's the graph in blue. That's the graph in red. And we're trying to find when the blue one is above the red one. Okay. First of all, is the blue one ever above the red one?
No.
Never? Like the blue one never goes above it?
Well, yeah, it does go above it.
Yeah, it does go above it at some point. So we have to find where that is. Okay. So what do you think we have to find on the calculator here?
Intersects.
Yep, we gotta find the intersection point. So I'll do second calc intersect. Move my cursor just kind of close to where they cross. It's good enough. And I have my intersection here. So how would I write my answer? Remember, this is an inequality, so the final answer is also going to have an inequality.
Bye.
Think they are? So what values for x could you pick to ensure the blue graph always stays above the red graph?
0.45.
What is it? 1 point what?
4 or 5.
Yeah, anything that's that number. Well, you said that number or higher. Can we include that number?
No,
No, why can't we include it?
because it wouldn't be above it.
Well, it wouldn't be above it, it would be exactly equal, and this specifically says it has to be above it. So you could pick any number above, we'll say 1.478, we'll round it off. So that's how you'd solve an inequality graphically. All right, so this one they want us to find domain and range. So to do the domain, we just have to be careful that we don't do what in the denominator?
0.
Yeah, we don't want to divide by 0. So let's figure out what numbers would cause us to divide by 0, and then say don't use them. So set the denominator. Well, actually, we can factor the denominator. How does x squared minus 4 factor?
X minus 2, x plus 2.
Yep, x minus 2, x plus 2. Now we should be able to figure out the two numbers that we can't use in the domain. What are the two numbers?
2 and negative 2.
Yep, 2 and negative 2. So if we think of that on a number line, 2 and negative 2, can we use anything lower than negative 2? Yeah, you can use anything lower. Could you use anything between them?
Yeah.
Yep, and could you use anything higher than 2?
Yeah.
Yeah, so there's 3 sections. The section lower than 2 is negative infinity to negative 2, not including it. What would the middle section be?
Negative 2 to 2, not including it.
Yep, negative 2 to 2, not including it. And what would the section on the right be?
2 to infinity, not including it.
Perfect. So that's your domain. Now, the range, we do need to graph it, because that's going to be a little tricky without a picture. Picture is going to help quite a bit. Okay, so here I've typed it in. Let me just fix this to 4. Okay, so here's our graph. And the range is how high and low the graph goes. So let's look at that. Does it go up forever based on what you're seeing there?
Yeah.
Yeah, because we've got some vertical asymptotes. We've got one there. And we've got one there, 2 and negative 2. Those are my asymptotes. So it does go up and down forever. But the question is going to be, does it hit everything in between going up and down forever? What do you think? It does go up forever and it goes down forever, but does it hit everything in between going up and down? No, there's a gap there. So let's figure out what this gap is. How low does it look like the graph is coming down in quadrant 1 and quadrant 2? It's coming down and getting close to what number?
0.
Yeah, it's getting very close to 0. Let's see if it reaches 0. So if we start plugging in like bigger and bigger numbers, right? Let's plug in like 20.06, 50.02, 500.002. So we're getting close to 0, but does it look like we're going to reach it? No, you're not going to reach it. So it gets down to 0. Let's check the other side too. Negative 50, right? Negative 250. Again, it's getting, let's see, on that one, it looks like I did get a negative number. I got negative 0.0039. Let's go to like negative 9,000.
On the left side, it looks like it's approaching like a negative 1. Because it's already overlapping 0.
Yeah, it's overlapping 0, so I'm trying to see how low it looks like it's going to go. Let me just plug in a really big negative number and see if I can tell. All right, so it looks like, looks like it might just keep dropping down on the left side. So that's a little tricky. Let's put in negative 900,000. Well, yeah, I don't like that one. Second table. Negative. If I keep putting in a bigger and bigger negative number, well, boy, that one's tricky. Let's base it off what we can see on the graph, all right? Because yeah, there's something a little weird about this one, because I did hit a negative value, which means it does go past 0. But let me put in an asymptote just by hand, and we'll pretend that it never goes past that line, just to simplify what's going on. Okay, so I'm going to put in an asymptote right there, and we're going to say that it doesn't go past 0. Now, the other part we have to look at is this part in the bottom. It comes down to 0, but it goes up to a certain number. How would we find how high this bottom part goes?
Find the maximum.
Yes, and that's part of finding local extrema. So I'm kind of tying two things in together. Second, calc, maximum. Let me do zoom 6 to just put the window back the way it was. All right, so let's do the maximum. Second, calc, maximum. Pick a point to the left, pick a point to the right, and do your guess. So it looks like it comes up to negative 1.2. That's what it comes up to right there. If we go to 2 decimal places, it's negative 1.1. Yeah, negative 1.20. Okay. So let's look at the range in this section. What's the lowest that this part goes?
Negative 50.
Yep, negative infinity. Up to and including, what's the highest that that part goes?
Negative 1.2.
Yep, and it does reach that, and I know it reaches it because I can see it on the calculator where the y is. It reaches it. All right, so that's the bottom part. Now let's describe the top part. How low, based on the asymptote that I drew in, how low does the top part go?
0.
0, and again, based on the asymptote, would it ever reach it? No. So it never reaches 0. And how high is that section going to go?
Infinity.
Yep, infinity. So when we're finding local extrema, just because we only did one there, remember this would be a local max, that would be a local min. If I ask you, what is the local minimum? I want to know the y value. If I ask you where the local minimum is, I want to know the x value. So what the minimum is, or maximum, is the y value. Where it occurs is the x.